You can see my screen. Okay, great. So like we are continuing the transformer. So like we are almost uh, close to the end of the transformer. So in the last class, we already have discussed transformer in great detail, but few of the things were left, and that we are going to cover now. So till now we have seen different components of the transformer. So we started with self-attention, then went through this positional encoding. Like even in the self-attention, we went through multi-head attention, then positional encoding, and then now we are going to see this normalization. So in this case, in the transformer, we do layer normalization, and this method, like this was given by the Hinton. So Hinton, like when he was taking some lecture, so in that lecture he explained it. So there is no any paper for this. So he has just explained in while like during his lecture, and this become very popular because this layer normalization is being used for RNN, LSTM, and even nowadays like in transformer. So it's like quite popular in this type of networks, like the networks related to the this NLP family, models related to the NLP family. Okay, so let's see like what is there in the layer normalization, how we do it. So before that, let's see like batch normalization. So we already went through the batch normalization when we were discussing the CNN part. So in the case of batch normalization, what we do, suppose, let us take the example. So suppose we have three samples. Suppose you are having three images, and you are having three images in a batch, okay, and you are providing to the model. You are providing to the your deep learning network, okay. So suppose this is the first image, second image, and third image. So it's like vector. So you are providing to the fully connected, so you know that you have to convert your input into vector. So this is the vector for the first sample, this is the vector for the second sample, this is the vector for the third sample. Now you are going to, now suppose you have given it to the network, and you got the, again you will be getting three different vectors through one layer. Suppose you have applied one layer, one fully connected layer, you got again three vectors. That is like the representation of these three vectors. So you got the new representation of all these vectors using your fully connected. Now on those output, you are going to apply the batch normalization that we used, like we already have discussed in the previous classes. And how we do it? We find the mean and standard deviation for each value. So we're gonna go in a horizontal direction. So we have like for each sample we have these number of values. So considering one value from every sample, you'll find the mean and the standard deviation, and then you'll normalize it. So we are going in a horizontal direction, okay. And this thing will do for the every row here, where we have the values of the particular index considering all those samples. So for every index, you are finding the mean and standard deviation, and then you are normalizing all these things using that mean and standard deviation. This is your batch normalization. Now let's come to the layer normalization. Now in the case of layer normalization, there is one change. Now what Hinton suggested, that instead of going in a horizontal direction, now we should go in a vertical direction. So you have three samples, and now what we'll do, we'll find the mean of each sample separately and the standard deviation of each sample separately. And then you normalize every value of this sample with the help of this mean and the variance. So what is the thing here? What is the change here? Now in this case, in the case of layer normalization, for each sample, you're finding separate mean and variance, and then you are normalizing that sample with respect to the mean and variance. So for one sample, you have only one mean and one variance. Now in this case, you are going across the samples. So considering every index, and then you're taking all those values, the values from different samples, considering the same index. Okay. So whatever index you are, suppose you are considering 0th index, then we'll be taking value from the 0th index, considering all those samples in that batch. And then you find the mean and variance, and then you normalize every value here. So here, like, you are spanning across the samples. In this case, you are doing this mean and variance, you are finding this mean and variance with respect to each sample separately. And this idea he has given, and it got become very popular. So here you are stabilizing the each sample separately. And why it is required? It is required because many times you could be having very less number of samples in a batch. In that case, you know that if you're having less number of samples in a batch, then there's problem. Then if you go with the batch normalization, it will not give you, you'll be not getting proper mean and standard deviation. So for getting proper mean and standard deviation, you should be having larger size batch. That's the one thing. And actually getting that size batch in the case of RNN and transformer is difficult. Even there, like, there's no meaning of batch in a proper, just like image. Here we can say like, hey, this batch is containing these number of samples, these number of images. Now here the meaning of each sample is different, because here you know that here batch, whatever samples you are providing in a batch, these are not independent samples. In this case, these are like every sample is independent. Here, every sample is dependent. So here, that actual batch meaning is not that much meaningful. And another thing is like when you are applying transformer, now you are doing the refinement of every vector or every sample with respect to every other samples that we have seen. Like when we were applying the attention matrix, what we are doing, we are finding the attention value of the particular selected samples with respect to all other samples. And then you are refining that sample with respect to every other samples, considering the attention weights. So even if I see one sample here, if I see one sample here, if I consider this sample, this is the output from one layer. Now in this sample, the like in this feature vector, so this is the representation of, or refined representation of the particular sample. So now in this sample, you have the information of all other samples also. Why? Because you have done it while applying this attention. So while doing the attention, you consider all other samples. So that's why here in a sample, you have almost all those important information from all other samples, which is not there in this case. Here, every sample is independent. They are working in an independent manner. Here, that is not happening. So that's why layer normalization is meaningful in this case, because even in one sample, you have the information of all other samples also. And if you normalize it, then in some way it will stabilize the training process. And why we call layer? Because this one sample, what you see here, this is coming from your particular layer. So this is the output from the layer. In this case, we were considering the every output value separately, but here we are considering all those output values, what you are getting from the particular layer. So that's why we call layer now, because we are working on a layer, because this is the output of the layer. So we are directly working on the layer. So because this is the full output that you are getting from the layer. And then you are trying to normalize it. In this case, if I consider one value, this is not the full output from the layer. It's just one small value, one output, like one part of the output that you are getting here. But in this case, you are working on a full output values that you are getting from the particular layer, considering the particular sample. So he has explained this thing in his lecture, and then people started to use it, and it worked very well in practice. So even in the transformer or maybe in RNN LSTM, people use it uh, instead of batch normalization. So this is like more helpful if you are dealing with RNN or RNN LSTM or transformer. Okay, so this was the last part of this transformer that I wanted to explain. So now let's see the full complete diagram of the transformer. So again, you know that we have encoder decoder part. So encoder part is this, and in this encoder part, you have a lot of encoder layers, encoder block. So this is the one block, second block, and it could be having n number of blocks. And in every block, you have self attention, then add and not add is like just residual connection. So even in the transformer also they have used residual type of structure, because you know that this is very powerful structure for training the larger network, for deep network. So that's why even in the transformer also they have used it, this add part and then normalization part, and this normalization is your this layer normalization. And afterwards, we have feed forward network. This is just fully connected layers. And then again, add a normalization. Now this makes one block. And you will be having the similar copy of this n number of times. And at the starting, like when you are giving to this, again, you are having words, maybe sentences. You will convert into multiple multiple words. And then each word will be converted into vector. And then that vector will be added with the positional encoding vector, and that will be given here input. You can see like here positional encoding is also getting added, so that position information would be incorporated in the input. And then again these all the things will be applied. And finally, like once you are done with the encoder part, then we'll go for the decoder part. Like this was the this was the initial architecture. So this you can see in the paper also, that Vaswani, the paper, the first paper that published in 2017. In that paper, you can see like this big architecture, like encoder decoder architecture. Now, from the uh, encoder is sending two information to the decoder, and those informations are key and value. And then query is coming from the decoder side only. So suppose, let us take the example. Suppose you have given, hey, take this sentence. You have given this sentence, and now you are going to ask something from this sentence. So from this side, you are saying, hey, you translate it in English, in maybe French or German, maybe French. So what will happen? This thinking machine, it will be processed here. It will get apply the self attention, everything, all the encoder blocks, and then from this side, key and value would be sent to the decoder side. And from decoder side, query will be produced, and query will be coming from here, because decoder is going to ask. So that's why query is coming from the decoder. So key and value are coming from the encoder side, and then decoder will ask the question. The query is like you are asking something, and you are asking from the encoder, like whatever you have got from the encoder, you are asking the things from that. Okay, so you got the key and value from here, and then you generated the Q from this side, and now again you are going to apply the attention. So in this case, your key value and query are not coming from the same input. Key and value are coming from the same input. Query is coming from the different input, because here you are giving different input. So when you have query, key, and value, if they are coming from the same X, then you will be say, and if you apply the attention here using these all the variables, then you can say, hey, this is self attention. But when your query is coming from different X, and key and value are coming from the different X, in that case, again, if you're applying the attention, then that will be called as a cross attention. Okay, because these are like coming from the different. Self means everything is coming from the same X, and then you are doing the attention, you are finding the attention weights and then applying the attention, getting the attention weighted matrix. But if the things are coming from the different x, and you're trying to you're finding the attention, that is called cross attention. Okay, so with that, transformer is more or less completed. Now I'll see one more application of the transformer, that is ViT. So I'll just give you the overview of that, and then we'll complete the transformer part. Okay, so actually this transformer became, when it came around 2017, that time it became popular, but it was not quite popular for the imaging task, for the vision task. But around 2020, when all those architectures, all those networks related to this vision domain, they got saturated. Then people have started to think what should we what should we add, or what should we uh, consider as a next architecture or as a next model. And then they got to they found that, hey, transformer is already there, so why not we should use transformer. But it was not easy to use it. Even if I ask you how should I use the transformer, then you could also give some idea. Hey, I know that we have image, and we know that transformer accept vector, so somehow your image should be converted into vector. Now if I convert this image into one larger vector, that will not solve the problem, because transformer wants multiple small size vector, so that it will process it in a sequential manner. It will try to capture the relationship between these all the vector. That's the purpose of the transformer. So you cannot convert into one vector and will give to the, even the size would be very huge. It will be, it cannot handle by the your self attention mechanism. Even one vector will not, that is not meaningful. So then thought of why not we should consider one pixel as a one token. That token is like one word. So the first idea would be why not we consider full image as a one word. But that is problem. It's there's problem there, because if you consider that one word, then that size of that word is huge, and it will be very difficult to handle by the transformer. And even here, in there's no relationship between, we are not giving focus on relationship between different images, because that's not the focus, because we are considering every image as an independent image. In the case of text, we know that words are dependent, they are related, but here things are not. We are considering each image separately. We are not seeing the relationship between these two images. Okay, that's not happening there. So that's why if you consider one image as a one word, then that will not help you. Then why not, then we could have very naive idea, maybe, hey, we can consider one pixel, maybe we can work on a pixel level and consider one pixel as a one word. Okay, so if I consider one pixel as a one word, then suppose if you have RGB image, then for one pixel you could be having three value RGB. And in this manner, suppose your image is maybe 256, or maybe consider 512 by 512, then you could be having these number of words, these number of tokens. I take this word and tokens, both are the same thing. So actually, whatever how you are giving input to the your transformer network, how you are dividing it, that will give you the tokens. So most of the time we consider one word as a one token or as a one sample. Okay. But sometimes even you can combine two words and consider as a token. So it depends. But whatever example I have given you, here we have considered one word as a one. So suppose we are considering every pixel as a token, then you could be having huge amount of tokens or huge amount of words. And now handling this amount of words is very difficult, because you know that whatever the size is here, suppose this is n size, your attention matrix, what you are going to calculate, the size of that matrix would be also of almost this size of n by n, not this size, n by n. So it's like huge dimensional 2D matrix. And it's very difficult to handle. Even complexity would be huge. So this idea is also not, again, at the pixel level, it's very difficult to, at the pixel level, you do not have much information. That's the also problem. Because if I just show you one pixel, you will be not able to interpret anything. So that's why working on the pixel level is not good idea due to complexity. And again, there is no meaningful information at the pixel level. So then the idea was just if you are not able to work on the pixel, if you are not able to work on the full image, then just choose the in between way, and that is your patch. So then this vision transformer came with that idea. So what it has done, it has converted image into patches. So take the image and divide into multiple non-overlapping patches. Suppose this, consider this one patch, then take second patch, third patch, fourth patch, fifth patch, sixth patch, seventh, eighth, and so on. And then each patch will be considered as a token, and then we'll process it. And they have done it. So this was the initial paper which came in 2020, and it like on archive, and then it published in ICLR 2021. And you can see like even this is not latest citation. Still, you can see like it's like 26,000. Nowadays, even nowadays you can see like even it will be, I don't know how many, maybe 30, 40,000 citation would be there, even more than that. So you can see like how popular this is. So when it came after that, people have started to, everyone started to use this vision transformer or variant of the vision transformer for solving different problems related to the computer vision. Okay, so I already said that naive applications image requires high computation. So you cannot go pixel by pixel, then divide into patch. That patches, each patch will be called as a token. And then like again, you know that transformer, when you want to train the transformer, you need large data set. So what they have done, they have pre-trained the ViT on very large data set. So they consider JFT 300M data set, and then they have pre-trained it, and then later they have fine-tuned it for the different other data sets like ImageNet Real, C400, VTab, and then they got this paper got these all the results like 88.55. This like they got very good results. Okay, so again, let's go through uh, the steps how it is happening. So given the image, suppose you have given the image, this is the image. Now you divide this image into multiple patches. You can see here, this is one patch, second patch, third patch. Now put all the patches here, like one by one. Take one, this, second, this, third, this, fourth, this, and so on. And then you know that your transformer accept vector. So each patch you have divided into different tokens. You have divided into different words, but that word should go in a vector form. So next thing is like you convert into vector. So it's like do the linear projection. Okay. So either you flatten it, make the vector, like open this 2D small 2D matrix, and then that vector you give here. So you will provide. So every patch will be converted into vector. Every 2D patch will be converted into vector, and then after that you are also adding the positional embedding, because somehow you have to also give the position information that is missing. So if you just go with the basic like vanilla transformer, then there is no position embedding or positional information. So for that, you know that you have to provide the you have to add the positional embedding, so that position information would be incorporated. And then once you do it, then go to the transformer encoder, just similar to the block that we have seen previously. So give to this, and then again this will give you the features. From this you will getting the different again different, we can say the uh, all those vectors as output, like refined vectors, and then you combine it. Maybe at the end you use one MLP, like your multi-layer perception, your fully connected layer, for doing the classification. So you can do the image classification using this vision transformer. So again, just even for the uh, more understanding, let us take one more example. So suppose you have given this 224 by 224 image. This is the image of frog. Now your goal is to convert into patches. And suppose I'm saying, hey, you consider 16 by 16 patch. So every like here, this image will be converted into different patches. So you can see at this point, uh, so you can see this is the first patch, second patch, third patch, all. So if you divide this into patches, so you'll be getting these like 14 this side and 14 this side. So total number of patches will be 196. Okay. Now you got 196 patches, and every patch is having size 16 by 16. So you can see. So this is the 16 by 16, and your channel is 3. So every patch is having dimension 16 by 16 by 3. So this is the size of the patch, height and width, and the channel is 3 because you are considering the RGB. And you will be having 196 such type of patches. Now you convert your patch into a vector. So either you can directly convert it, maybe flatten it, and then you flatten every 2D matrix, make the 1D vector. It's very simple method. Or you can even use convolution layer for doing it. That will divide. That will like it will also do the same only. So either you can do manually or you can use convolution layer to do it. But when you do it, after that, what will be getting? You'll be getting 196 patches, 196 tokens, and each token is having dimension 768. Why? Because you have converted this 1616 into 3 matrix. If you multiply these all things, it will give you 768 value. Okay. So you got 768 value. Okay. Now, and you have this 196 such type of embedding. Now we also consider one extra vector, or one extra this we can say token, and that is called CLS token, classification token. So in this token, you can see like one token is containing the information of one patch, and we have 196 tokens. So 196 tokens are containing the information of all those 196 patches. We consider one extra token who will contain the average information from all these tokens. And so that's why this is called classification tokens. And generally we use it to give the MLP layer for doing the classification, because it is having the average, it is having the aggregated information of all these patches or all these tokens. So let's see the full diagram. So image divide into patches. Now convert each patch into vector. So we'll be having the linear projection layer here. You can see we are converting it, every vector, and add one extra token, that is your classification token. So we got 196 tokens from the image, and we have added one extra that will make the 197. And then every token you'll be adding positional embedding also. So every token will be having different positional embedding vector, and that will be added there. So it will be added there, it will be added in this will be added in this. And once you do it, now you have converted your input into the form which is acceptable for the transformer. Because this was the form that we have seen when we were dealing with the text-based task. So here also you have made the things in a similar manner. So now you can use transformer encoder. So this block would be similar to the previous one only. So here again, you will be having all those layers, self-attention, multi-head attention, then all those add normalization, fully connected, everything would be there. And at the end, whatever you are getting here, maybe whatever refined features you are getting here, you can even you can aggregate it, or maybe just take the CLS token, because that is having the aggregate information. Just take it and give to the one more fully connected layer, which will do the classification, like which will give you the probability value. Maybe if you have 10 classes, then it will project to the 10 values, and you will get the 10, all those 10 probability values, and then it can accordingly, like you can find the loss and then do the backpropagation. So at the end, you can do the classification. So like they have done the experiment, and they took the different variants of the ViT. So like ViT base, ViT large, ViT huge, and so ViT base is having 12 layers. Then it is having 24 layers. ViT huge is having 32 layers, and then this these are the different other information. These are the parameters, like 86 million parameter, 307 million parameter, 632 million parameter. Again, they got, these are the different data set on which they applied this ViT, and they got promising results. Again, they visualize the attention, like what is happening inside the attention, how, like what it is, what it is trying to learn. So after visualization, what they observe, that when you are giving this input, it's giving the attention attended output that you are getting, it's giving this. When you are applying this, this is giving this. So somehow it's trying to learn the information which is useful for the doing the classification, because your goal is to classify this image, and your area of interest is this side only, because this is the main object. You are going to decide the class of this object. Even in this case, you are going to decide the class of this object. So when you are applying the multi-head attention, so your attention is somehow trying to learn the important information which is required for doing the classification. So after getting, when you are applying the attention and whatever features you are getting, if you visualize it, you'll be having maybe this type of stuff. Like the focus would be on the area of interest side, like the attention would be on the object which is useful for doing the classification. So this is the ViT that we have already I have already explained. So with that, ViT is done. Okay, I forgot to explain few more concepts, a few more variants of the transformer, and those are like this BERT and GPT. So let's go for that also, so that this will be fully complete. So here, like I stopped here, but and I have shown you the one example. Like I moved toward the ViT, but also see few variants of this transformer. And the first variant is BERT. Now, what is BERT? So actually, initially the initial paper which came, that paper was having it was having both encoder and decoder. Then people realized that, hey, why should we use both encoder and decoder? Why not only encoder? Why not only decoder? So this BERT came, and BERT came up with the idea, like it says that, hey, I'll be using only encoder. So BERT is like a stack of encoder blocks. So whatever you have seen there in the encoder side, you're just taking the encoder side, and that is your BERT. And how the training is happening here. So what BERT is doing, BERT is like, it is, the full name is bidirectional encoder representation from the transformer. So what it does, BERT jointly encode the right and left context of a word in a sentence to improve the learn feature representation. So it is trying to learn the left and right context both. And how it is happening? So for that, it is training this architecture in that manner so that it can learn it. So for the training, it is having these two type of strategy. First one is masked language model. Okay, so this is done like in a self-supervised manner. So what they are doing, whatever input they are having. Suppose we are giving the sentence. Suppose we are having the sentence. Now in that sentence, this method will mask 15% of the words from this sentence, and then it will give to the model. It will give to the this encoder, this transformer encoder, and then it will tell the transformer to predict it. So whatever words have been masked, now the job is to predict it, like what was there, what are the things were there. So it's like you're just masking. Maybe I'm saying, hey, this is a, and then I remove the cat dash here, maybe a dash here. It's just like filling the blanks. And now you're saying to model, hey, you fill this, and then again your model will fail. Initially, it does not know like what it has to predict. But once this gives the result, it will be maybe first time it will be wrong. But you have the actual word also, because you have created this input from the given text only, from the given sentence only. So we have this sentence with you, and now you know this what should be here, what should be here, what should be here. Again, you find the distance and minimize it. And in this manner, it will learn like what should be the next or what should be the behavior. So it's learning both the context. Even you could be having maybe this, maybe dash or cat. Here, for learning this, for understanding this, it has to see the left side also, right side also. So in this manner, it's trying to learn the sentence, trying to learn the this language, how the things are arranged, how the things like what should be the, like when something is missing, how to fill it. So slightly like somehow you are trying to learn it, it is trying to learn the language. So this is one way. Second way is like next sentence prediction. So here, like in this first case, somehow it's trying to learn the sentence. So if something is missing here, then it has to put the information there. Now in the next part, this is like next sentence prediction. Here, what we do, we make the pair, okay, and we give pair to the this encoder blocks, encoder transformer. So we'll give the pair A and B, and model has to predict either 0 or 1. So if it is predicting 0, then it's like this pair is not valid, or it could be vice versa also. So whatever value you are taking for, so suppose you are taking 0 for the invalid and 1 for the valid. So if your model is saying, hey, when you are giving A, B and it's saying 1, that means these pairs are valid. When it is giving 0, then these pairs are invalid. Now how you are deciding valid and invalid? So valid means like when I'm writing sentence this, suppose I'm giving this A, and if I'm taking the next sentence as a B, in that case, this pair is valid, because this B is coming after A. It's like following sentence. But if I'm taking A from here, maybe first sentence is A, and B I'm taking randomly from anywhere. In that case, that A-B pair would be invalid, because B is not the following sentence. So we make this pair for the training purpose. So pair is formed such that B is actual sentence next to A 50% of time. So 50% pair would be valid and 50% pair would be invalid. That is like your training data. And valid means B is following the A. B is coming just after A. And when it is invalid, that means B is random sentence, which has been taken from like anywhere, like it's just random sentence. So that is like your invalid pair. And now model has to understand it. So when you are giving A, B, and if that pair is valid, then model has to say, hey, this is valid pair. So in this way, your model is trying to learn the language, because one sentence, another. So it's trying to learn the relationship between different sentences. whether they are close, whether they are valid. So somehow trying to learn how the sentences are arranged. So yes, so these are the two things that we generally do for for training this BERT, and this is like pre-trained. So it's like you're making the model. Now this model you could be using for different type of tasks. So suppose you want to do the sentiment analysis, then you have this model which already have been trained in this manner. And now you take it and fine tune it for solving your problem. Because this model knows the language, because you have trained it for doing the same. And why this is called self-supervised? Because you are not generating ground truth, you are not getting ground truth from anywhere. Like you are generating by yourself only. So in this first case, you have given the text and you are taking this text as a ground truth, and then you are making the input from here. So you are not having, like you are not given input and ground truth pair separately. You are creating your ground truth by yourself. You are creating your input by yourself. So that's why this is like in a self-supervised manner. So this is your BERT, and BERT is generally used for doing classification, sentiment analysis, different type of works related to text. So you can see here, this is the BERT. Now let's come to the GPT. Now GPT is like stack decoder blocks. So GPT focus on the decoder, BERT focus on the encoder. And even what I told you, like that ViT, ViT is also using the like it does not use both the parts. So it's just use the encoder part, because one part is sufficient. We don't need both the parts. So nowadays, like some of the models are using the first part, like encoder part. Some of the models are using decoder part. So in this GPT, it's like stack decoder blocks. So we have the decoder. They have used the decoder block. And when I'm saying decoder block, then your you are like you're having your query key and value will be coming from somewhere else, and query will be coming from here. And then again, it will be using the attention, and then so it's just like whatever chat GPT, whatever you have seen, those are like based on the GPT only. So in the chat GPT, you are asking whatever you are asking, that makes the query, that is that information you are providing. And what it is doing now, it will take this query and it will generate the key value from the information that is there within that transformer. So maybe the database that is there, because again, it will fetch the information from the database, and while training you have to provide the information, the the suppose you are asking things from the PDF. So PDF, the key and value would be generated from the PDF, and then you are asking question. So you are asked, that is your query. So now Q will be generated from your question, and then it will go and find the attention with key and then multiply with the value, and that will give the refined output, and finally you will be getting your answer. So many times we use cross attention. So query is coming from different sentence, and key and values are coming from different place, from different text. For the generation of the text, generate this 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 paragraph, or generate this maybe page, or generate the, maybe you can also ask here, generate the story. So whatever you want to generate, you can generate it using your GPT. And you are for that you are giving prompt, you're asking question, and that is the query. And it is also having key and value, which is coming from somewhere else. And then this will be multiplied here, and then it will give you the final answer. Again, it will apply all those attention layers and all those decoder layers, and finally it will give you the final output. Okay, so these are like two things. Again, if you're interested, go and watch it, this BERT and GPT. These are like just variants of the transformer, but things are all, whatever we have discussed, almost like these two architectures are using almost like all those components what we have seen. So this is not the separate thing, it's just the variant of the transformer. So one is taking the BERT part, one is taking the encoder part, that is your BERT, and one is taking the decoder part, that is your GPT. And the goal of these two variants are different. BERT is generally used for doing the sentiment analysis, maybe predicting some missing information, or maybe some you can use for some other type of applications. Now, GPT is mainly used for generation task. So when you want to generate the text, when you want to generate some paragraph or maybe some story or maybe some new thing, then you will be using GPT. Okay, so with that, transformer is like we have completed the transformer. Now, next topic, maybe in the next class, we'll see encoder, encoder decoder. It's not like because this encoder decoder, whatever you have seen here, is almost similar type of structure only, but that encoder decoder came early because transformer came later, like 2017, but encoder decoder was there before that. So it was at that time people were using it for like using it for different type of computer vision task. Even for NLP also they were using it. Even you can also use encoder decoder architecture for considering the LSTM, RNN, or for the vision side you can use encoder decoder architecture considering the CNN fully connected. So anywhere you can use this encoder. So encoder decoder is just like you're making the design, and inside the transformer layer or LSTM layers or CNN layers or any type of layers you can. So we'll cover into that thing in the next class. So now I'll I'll allow you to speak. If you have any question you could ask. Can you hear me? Any question from this whatever I have discussed today? Is there any question from this? Things were not that much because we already have covered most of the things in the last class only. This was just the concluding or like conclusion of that work, just considering few more things. Otherwise the most of the things we already have covered in the last class, so that's why still if you have any question you could ask. So whatever new architecture, new models that you are seeing nowadays, most of the models are based on some variant of the transformer, either GPT or BERT, or maybe it could be having different variants of the transformer. So this self-attention, it changed the world. So now everyone started to use this self-attention. So because your transformer is like just self-attention mechanism. Otherwise, things are very similar to the other type of layers only. But this is like this self. Yeah, please mute it. So this self-attention makes this makes the difference for this transformer with respect to other architectures. That is your self-attention. So self-attention is the main component of the transformer. Otherwise, things are like feed-forward network. You have seen 1,000 times. This is your fully connected network. There's nothing. There's no new thing here. Add lot of time you have seen normalization. It's not new thing. Yes, they have used it in a different manner, but otherwise normalization already batch normalization you have seen. Only the part which is making this as a different, that is self-attention. And now this self-attention has changed the world. So this is the takeaway from this transformer. So even if you're going for LLM, like large language model, vision language model, whatever models you are going to try, you are going to use for solving some problem, you will be using, most of the time you will be using some variants of the transformer. And if you know how it is working, then at that time you'll be appreciating it. And again, you can also think some idea, maybe some changes. Otherwise, you will not able to change. You'll be not able to make some changes in the architecture. So for that, you need to understand. You need to know the basic, the mathematical things of this. Otherwise, you'll be considered this as a black box only. But now at least you guys went through the lectures. You have seen this transformer in a great detail. So at least you have, now you should not consider this as a black box. Okay, so I'll stop here. No, if there's no question, then I'll stop here. Uh,
Yes, sure. Thanks, everyone.
yeah, thank you.
Thank you, sir.
Thank you. Thank you.